Welcome back, everyone. In this Google Colab notebook, we're going to look at a simple example of how LoRA can actually speed up training and make it more efficient. You do not have to follow along because this is just a quick demonstration of a simplified LoRA implementation before we do a deep dive into our code on SageMaker. And so what we're looking at in this experiment that compares two ways to train a model, a full tuning versus LoRA. The model itself is a simple linear layer that is learning to perform a multivariate linear regression task. Okay, so now I'm just importing some basic stuff over here. I'm setting the seed so that it's reproducible. And obviously we don't have a data set, so we're going to be using synthetic data. And K, remember, is the output dimension. D is the input dimension. They're both 128 by 128. And R, which is 32 in this case, is 32. That's the rank. And remember, we talked about ranks and the trade-offs between a smaller rank versus a bigger rank and how that affects the number of trainable parameters and efficiency as well. Now let's suppose we have W base, which is our pre-trained frozen weights. Remember, we do not want to compute the gradients on this matrix, right? We want to create two smaller matrices, B and A. So the dimensions of the frozen weight matrix is K by D. So it's going to be 128 by 128. And as you can see, I'm already printing these stuff over here. Now the dimensions of A true, which is going to be one of the smaller matrices, is going to be 32 by 128. Now for B, it's going to be 128 by 32. And W true is going to be basically, if you remember our PDF that we looked at, is the, if we come over here, is essentially going to be the W effective. Okay, so it's the W that we use. We're going to add to it, we're going to add the frozen weight, and we're going to add that to the matrix multiplication of B true by A true. And if you skip the previous optional video, remember this means matrix multiplication. And so this is essentially it. And now if we call the shape on W true, remember, it's going to have the same shape as W base, because that's the only way we're going to be able to add to it. But it's made up of two smaller matrices. But if we multiply the two smaller matrices, that will give us the same dimensions as the original large frozen weight. But it's still a lot more effective to train two smaller matrices, right, than the one big one. Now, what is N? N is equal to 10,000, and our dummy data set is going to have 10,000 samples. X is the random input that's going to have a size of 10,000 by 128. And remember, it has to be 128 because that's what we defined the W base model. And so think of it this way. We have 10,000 samples, and each sample has 128 features. Okay? So each input has 128 features. And now Y is going to be X, which we just defined, the input, multiplied by W true, and W true is over here, dot T, and then we call the transpose on it. In the previous example, we looked at transposing with the dot T, but over here, this is more effective for these kind of data sets where you do the dot T and call it. And over here, actually, I don't even need this because we looked at that shape. Over here, this Y, if you do over here, you do Y dot shape and you print it, you're going to get 10,000 by 128. And the 10,000 by 128 is the number output of the model. Okay, so it's the output dimension of the model, and actually we don't even need this. So that is going to be the output shape of your model. And sorry, I kept on repeating that. I was just a little confused as to why we have two hashtags here, but I remember because previously this was not commented out. So excuse me for that little side tangent, but now you know that Y shape, which is the output of your model, has a shape of 10,000 by 128. And this is because this is a multivariate regression, which means that you're going to have multiple continuous outputs. So if this was, something else, like when you need to predict one value, like the price of a house, then the output would look like, we had 10,000 samples by 1, right? Because for each sample, you have one output. That's the price of the house. But for multivariate regression, we basically have multiple outputs. So we have 10,000 samples, and each one has 128 outputs, okay? Now, if you don't know what multivariate regression is, don't worry about it. Do a quick Google search or ask ChatGPT or whichever LLM you use. But just know that it has multiple outputs. But please don't get hung up on that, because that's not the point of this video. You can very much understand LoRA without understanding multivariate regression. This is just how I set up this example. Okay, so now that we understand the input and the output shapes, let's go on and see what's happening. So over here, we're going to have two models. One is going to be a LoRA model, and one is going to be a simple full linear model. Now for the LoRA model, we just basically create a neural network module. So from PyTorch, that's the nn.module. We create a module we inherit from the nn.module, and then it's going to take two inputs, the W frozen and the rank. Okay, and remember, W frozen is going to be the original W base that we input to it, and the rank is going to be, how much parameters we want to tune. We call super.init, and then over here we get K and D, and that's going to be from wfrozen.shape. And K and D are going to be 128 by 128. It is from W base, and K is the output and D is the input. So by calling .shape on wfrozen, we get the values of K and D, and we're going to need that because that's going to be how we construct the two smaller matrices. Okay? And if you don't know what wfrozen is, don't worry about it. But once we call the models, as you can see, we call it with wbase. Okay? And wbase is just this frozen model. Not frozen model, sorry. It's just this weight matrix with the frozen weights. Okay? So that's what wfrozen is. And now we do self.register buffer w and w underscore frozen. And this attaches a tensor to your model, just like a parameter, but it marks it as non-trainable, right? Because we do not want to calculate gradients for w frozen, okay? And now here we have self.a and self.b. Now, the nn.parameter wraps the tensor as a trainable parameter in PyTorch. Okay, so that's why we do nn.parameter. And if you look at it, I'll talk a little bit about why we add the 0.01 here. But if you look at it, this creates a random tensor or a random matrix of size, the rank, which is going to be 32 for us, by D. And remember, D is 128. So 32 by 128. And over here for the B matrix, this is going to be K, which is 128 by 32. Oops, 32. Okay, so once we multiply B times A, it's going to be a valid matrix multiplication. And at the end, it's going to be the same dimension, 128 by 128, as the original W base. So we're going to be able to add it to it. Now, what is this 0.01 over here? Well, this is a core idea of LoRA, and you need a small 0.01 so that B matrix multiplied by A matrix starts near 0. So the initial output when you multiply B times A is going to be approximately equal to the W frozen, okay? And W frozen is the W base, okay? And the reason we need it to be approximately the same is because this prevents large updates and it keeps the gradients and outputs stable early on. And LoRA is about small corrections, not replacing the whole frozen weight matrix. So without the small 0.01, your model could overwrite pre-trained weights too aggressively, and it becomes unstable during training. Okay? And even though this is a synthetic example where W frozen is randomly initialized, using 0.01 is a best practice so that you understand why we're adding a small 0.01 to it. Okay? And that will ensure that the multiplication of matrix B by matrix A are going to be really small numbers, so that when you add it, essentially remember, when you add it to the W base, it's not going to be a huge update. Because remember, this is the forward method. We do X, which is the input, and so you multiply input X with the transposed sum of the frozen weights W and the low rank update B times A. So if I hadn't added this small 0.01, then these two matrices, when multiplied together, could be, could have very large values. And so they would override the original frozen weights. And why do we not want to override it? Well, because remember, this has already been trained for many, many days or hours on large GPUs. So we don't want to lose that crucial information. We just want to fine tune it to our use case, okay? So we don't want to override the frozen weights too aggressively. We want to gradually, incrementally add to it, okay? So I hope that makes sense, that we just call the forward method. And essentially over here, this is what we talked about a lot, okay? So we add to the self.w, and we add to it the B multiplied by A. And remember, A is the small matrix, B is the other small matrix, and W is simply going to be the frozen weights. Okay, so that's what we're doing over here. And now here we have the other model, and the other model is simply just a fully linear model. We again have nn.parameters and winit.clone. What is winit? Well, when we call this full linear model, we just inputted the W base. Remember, this doesn't have a R because this is not LoRA, and we just conduct the forward path, which is X multiplied by the weights. Okay, so I hope this makes sense, and we will continue in the next video where we see what happens.